Hi again. In this lecture on quantum error correction with germanium Hall spin qubits, I've already covered two parts, classical error correction and quantum error correction. And I was focusing on very simple theoretical ideas on how to perform error correction. And in this last part, I will highlight some recent experimental progress into this direction and also some future challenges. So I'd like to focus on this experiment, a rudimentary quantum error correction experiment with Hall spin qubits in germanium. And before showing experimental data, I'd like to show you the quantum circuit which was used in this experiment to perform quantum error correction. So in fact, the device is shown here. This is a 4-qubit device. So in the middle, you see this 2x2 block of 4 qubits. And on the side, you see S1 and S2. These are actually charge sensors which are used to read out the qubits. And the circuit, which is used for the quantum error correction demonstration, is shown here. It actually has these 4 qubit lines and shows you the gates and also the readout point of this experiment. So now there are 3 important differences between this circuit and the previous circuit, which I shown at the end of part 2. And let me go through these 3 main differences. So in part 2, in the quantum error correction circuit, I had a 5-qubit circuit where we had 3 data qubits and 2 measure qubits. Now you see that essentially in this circuit only 3 qubits are used and not 5. A second important difference is that in the previous part, I discussed an error correction scheme where there were measure qubits. Measure qubits were measured, and also there was active feedback applied. So depending on the measurement outcome on the measure qubits, there was some active error correction happening on the 3 data qubits. And now all this is gone and represented or reduced to a Toffoli light gate. So with certain tricks, one can start from these canonical error correction schemes where you have measure qubits and you have active feed-forward mid-circuit measurements and active error correction, and tailor it to smaller devices when you don't want to have like 5 qubits. So you can also make this choice that you simplify the circuit in this way that this consists only from coherent operations and there's no feed-forward required. The third major difference here is that in the previous part, I was talking about an error correction code which is robust against bit flip errors. But here in this circuit, you see here that these are the errors. These are the Z errors or phase flip errors and not bit flip errors. So this is a different type of error. But similar repetition code type circuits can correct this type of Z errors as well. So these are the 3 key differences. And maybe I should also warn you that in the circuit diagram, whenever you see a Y or a Y inverse operation, that's a single qubit gate, but it's not following exactly the canonical notation, because here Y means a 90-degree rotation around the Y-axis. The Z gates do follow the canonical notation, so Z means actually a 180-degree rotation. Let me show you the experimental data which is coming out from this circuit. So here on the x-axis you have the error probability P. So this is the probability of the Z error or the phase flip error, which we have seen in the previous slide. And in this experiment, this was a control parameter of the experiment, so it was tunable by the experimentalists. And on the y-axis, you see some kind of a figure of merit. It is called the state probability gamma. So this is a figure of merit which is quantifying the performance of the error correction scheme. Perfect performance corresponds to 1. And if this value is smaller than 1, that means that there are imperfections in the functionality of the error correction scheme. And so actually the inset is showing a similar graph than the experimental data itself. Again, x-axis shows the error probability P, y-axis shows this state probability gamma, and this is showing results for an idealized scenario. So this linear curve starting from 1 and decreasing linearly corresponds to a non-corrected qubit. And then this other one, this black line gamma ideal, corresponds to the performance of an idealized error correction experiment. And the major difference, of course, is that the starting point of this black curve, this is not linear, but it has a parabolic dependence, quadratic dependence to start with, meaning that in this ideal scenario, the error correction scheme actually is indeed reducing the errors characteristic of the physical qubit. And so the experimental data is shown as the points and the error bars here. And the main point I want to make here is that this is really like a systematic, reasonable dependence of the state probability gamma on the error probability p. As the error probability p grows, the state probability gamma goes down, meaning that the efficiency of this error correction scheme is going down, which is of course in line with what you predict from the theory side. Of course, we also have to note that this experimental data is very far from an idealized or useful scenario, in the sense that, for example, at the starting point when the error probability p is 0, the state probability is not 1 as in the ideal case, but it starts from 0.65. So it's important to note that this experimental data or this experiment is not yet beyond the break-even point. So this error correction scheme is not producing qubit, a logical qubit, which is better protected than a physical qubits in this setup. But nevertheless, it's a nice demonstration that you can assemble a fairly complex combination of all these gates and single qubit gates, 2 qubit gates, 3 qubit gates, and readout procedures in such a way that you get some reasonable systematic experimental data coming out of this. So these were some recent achievements, recent progress, and in this final slide, I'd like to summarize once again what has been achieved so far, and also I want to point out future challenges that should be overcome. So as I argued, in germanium whole spin qubits, there is a highly advanced technology and machinery to initialize quantum bits, perform single qubit gates, 2 qubit gates, 3 qubit gates with high fidelity, and also to read out these quantum bits. I have illustrated the first quantum error correction experiment, which was carried out by the Delft group recently on a 4 qubit processor in a 2-dimensional array, a 2x2 qubit array. And also I'd like to point out that there is recent progress also on scaling up. So recently the Delft group demonstrated a 16 quantum dot device. They were able to tune it up. It's not yet operating as a qubit register, but nevertheless it's still a big step to scaling up further. Of course, there are also challenges to bring this field forward. An important outstanding challenge is to improve coherence and also improve fidelities of initialization and readout and gates. It would be a very important milestone to reach the break-even point for quantum error correction, which could be potentially done also with a similar device and similar circuit as this previous experiment was done, but with increased figures of merit, increased performance. And of course, an important goal is to scale up these systems. A goal of scaling up could be either to achieve better and better quantum error correction schemes, better and better protected logical quantum memories by incorporating more and more qubits in the array. But also if one wants to move towards useful quantum advantage, either with NISQ algorithms or with quantum error correction, it's inevitable to scale up the current. With this summary, I'd like to stop here and thank you for your attention.